This is PreAP, PreCalculus, and we are beginning with the first chapter, logically. Section 1.1, shifting, reflecting, stretching graphs of functions. And we are looking at graphical and analytical approaches. There are many, many types of graphs that we call parent graphs, because if we know what the parent graph looks like, we can take any of their babies and graph them fairly quickly if we know some special rules. Now, we're going to get to those special rules in this section. But before we get to them explicitly, I'm going to come at you sideways here first. Let's check out the basic square root function. Let me give you the rationale of where these ordered pairs come from, and then we'll graph them. If I were to simply make a simple t-chart, an xy chart, where y is the square root of x, if I put a number in for x, I'm going to carefully choose numbers to put in for x that are perfect squares. For example, 0 is a perfect square. Its square root is 0. 1's a perfect square. Its square root is 1. 4 is a perfect square. Its square root is 2. 9's a perfect square. Its square root is 3. So to be clear, in each of these cases, if I put this number in here for x, the square root of x ends up being this number. If I put those ordered pairs on this coordinate plane, we got 0, 0, 1, 1, 4, 2, 9, 3, which would be right about here. Keep in mind, we can't put negative numbers into this because if you square root a negative number, it becomes imaginary. So our graph starts at 0, 0, and it moves like this. It moves to the right much faster than it goes up. See if I can make that a little bit nicer. Good enough. It is a curve. It has a vertex at 0, 0. That is the basic square root function. That is the parent graph. What would happen if I took this function and I added a 2 to the outside? How would that affect the graph? Let me tell you exactly what would happen. It would move the graph up here like this, where the vertex is now at 0, 2. That would translate the graph up 2. Now you can look at that equation and you can try to come up with a conjecture of what is it about this that makes it translate up 2. We'll talk about that explicitly here in a moment. What would happen if I were to take this graph and I were to subtract 2? It would come down here like this, with the vertex being 0, negative 2. This would translate the graph down 2. Now, if I were doing this by hand instead of just copying this and pasting it over, I would start it the same way. I would say, well, how does the parent start? Well, the parent starts here at 0, 0. Since I know this is translated up 2, and we'll get to that in a moment, how we know that, I would start here at 0, 2. Once I'm here, I do the same thing that I did when I was over here. Go to the right 1, I go up 1, because the square root of 1 is 1. From here, I go to the right 4, and I go up 2. Just like here, we go right 4 and up 2, because the square root of 4 is 2. Square root of 9 is 3. Square root of 9 is 3. Once you know where your vertex is, your starting point, we don't really concern ourselves with this translation. We just go as if this was the origin. D, what happens if we add a 2 on the inside of the function? Well, it may not do what you think it does. It actually is going to move the graph to the left 2. So this would be translate left 2. Once again, once I know the vertex is here at negative 2, 0, I would then pretend like this is the origin. If I put a 1 in, the square root of 1 is 1. If I put a 4 in, the square root is 2. If I put a 9 in, the square root is 3. Let me write this a little more legible. What happens if I subtract a 2 on the inside? That is going to take the graph and it's going to translate it to the right 2. What if we were to multiply the outside of the function by -1? That is going to cause a vertical reflection. So anything that's above the x-axis now is below the x-axis. Anything that's below the x-axis in the parent graph would now be above it. So the vertex, well, that's at 0, 0. If you reflect something over the line of reflection, it doesn't move. Normally we go to the right 1 and up 1, but now we're going to go right 1 and down 1. So the square root of 1 is 1. Square root of 4 is normally what actually is 2. Since it's a reflection, we're going to come down here at -2. I'm going to go to the right 9. Square root of 9 is 3. We're supposed to do a vertical reflection, so we're going to go down 3. So this graph will look something like this. What you want to be thinking about when we're going over these things, how did I know this translated to the right 2? What about this equation told me that? What made me go to the left 2 in this one? What made me do a vertical reflection in this one? Continuing. G, we're multiplying the outside by 2 and we're multiplying the inside, x, by -1. So let's see. I'll tell you what it does, and then we will see what it does graphically when we actually look at the picture. This here is a horizontal reflection. This here is a vertical dilation by 2. Let's discuss each of these individually. Do not graph this first thing I'm going to graph because it's not the answer to this. But if we just were to reflect it horizontally, that means we're reflecting it over this y-axis. 0, 0 isn't going to change because that's on the line of reflection. Normally we go right 1 and up 1 for a square root function. Since it's reflected horizontally, we're going to go left 1 and up 1. We're going to go left 4 and up 2. We're going to go left 9 and up 3. So it would look like this if in fact it was just a horizontal reflection. A vertical dilation by 2 means we take every y value, this one, this one, this one, and this one, and all the points in between that we haven't named, and we double them. So I'm going to draw this in blue, then I'll get rid of the red one. If I double 0, I get 0. If I double 1, I get 2. If I double 2, I get 4. If I double 3, I get 6. So here's how this would look. And let's talk big picture what this does again. Horizontal reflection means we go left instead of right. Vertical dilation by 2 means we go up twice as far as we normally would. Normally we go normally we go right 1, up 1. Now we're going left 1, and we're doubling how far we go up 2. We're going to go left 4, square root of 4 is 2, we double it, we get 4. Square root of 9 is 3, we double it, we go up 6. Now once again, ask yourself, how do these numbers, the 2 and the negative, how did that affect this graph? We will get into that formally. Multiply the inside by -1 and subtract 2 on the inside. Well, I don't like how this is written. In fact, I hate it. We don't ever want the coefficient of x to be negative. Here's how we're going to rewrite this. We're going to rewrite it as the square root of negative times the sum of x and 2. We want it like this. We want the coefficient of x always to be positive. Now you might be saying, well, it wasn't positive over here. That's true, but we could have rewritten this as 2 square root of -1 times x. Technically, the coefficient of x is the 1 that you see, that you don't see here, and then we're multiplying it by -1. You'll see as we continue, we always want the coefficient of x to be 1. That's especially true for adding or subtracting numbers. So here's what happens here. There's a horizontal reflection again. So that means instead of going right, we're going to go left. Had the parent graph went left, we would now be going right. We're also going to be translating left too. If I find my vertex first, my vertex is normally at 0, 0. Horizontal reflection doesn't affect it. If I go left 2, it's going to put my vertex right here at 0, -2. Now we've taken care of the translating left. Let's do the horizontal reflection. So instead of going up to the right one and up one, we're going to go left one and up one. Because the square root of 1 is 1. So from here, we're going to count to the left 4. 1, 2, 3, 4. Square root of 4 is 2. So we put a dot there. There's really not room to go left 9 and up 3. So we'll just draw this like this. Next one. Once again, I don't like this negative coefficient inside the function. So I'm going to factor that out so that it's x minus 2. This is going to result in a horizontal reflection and a translating right 2. If I translate to the right 2, my vertex is at 2, 0. You know what? I wrote this wrong over here. I wrote 0, -2. It's -2, 0. I'm just going to check my other ones. All right. It appears to be the only one I made a mistake on. Horizontal reflection means we're going the opposite way horizontally. So instead of going right, we're going left. So we go left 1 and up 1. Square root of 1 is 1. From here we go left 4 and up 2. Square root of 4 is 2. We go left 9 and up 3 because the square root of 9 is 3. So our curve would look something like this. Now, based on the observations that you just made, you made some mental notes about things. Let's see if we can predict what's going to happen with these graphs, and then we'll state the changes that were made, and we'll see if we can graph it. We're going to also state the domain and range of these functions. So first things first, I'm not going to sing it. We want to make sure the coefficient of x is a 1, and it isn't. It's negative. So let's factor a -1 out of the subtract the negative x plus 1. It's going to give us x minus 1, and then a -3. When we do these, we always want to do these in the same order. We're going to do them in the order of reflect, dilate, translate. How are you going to remember that's the order? Right here, RDT, really dumb teacher. Really dumb teacher. Really dumb teacher. That's the order. Are there any reflections in this? Well, there sure are. There is a horizontal reflection. I'll tell you what, I'm going to erase this 1, just make that negative in front. Reflect, horizontal. Any dilations? There is a dilation, vertical by 2. Any translations? Sure are. There's a translation to the right 1 and down 3. So horizontal right 1, vertical, down 3. Now, we've written that. When it comes time to actually doing it, I would start with the translation. We want to find this vertex. The vertex was here at 0, 0. We're going to go horizontally right 1, and we're going to go down 3. So our vertex is going to be right here at 1, negative 3. Now we're going to factor in the horizontal reflection and the dilating vertically by 2. Horizontal reflection means that we're going to go left instead of right, because the parent graph always goes to the right. And the vertical dilation by 2 means every time we go up, we double how much we go up. So normally I go right 1, up 1. I'm going to go left 1, up 2, because it is a vertical dilation by 2. Going to go to the left 1, 2, 3, 4. Square root of 4 is 2. I double it, puts me here. Start here. I go to the left 9. Square root of 9 is 3. I double it. That puts me here. Notice when I did this, I wasn't actually looking at any of the ordered pairs that would make these points. I'm just counting spaces. Just counting spaces. There is a way to do this with ordered pairs. We will get to that at some point. Some point today, hopefully. All right, so here's something that it's a good skill that we want to cultivate, and that is actually following the directions. And I did not do a good job when we read the directions, so let's read them again. Based on your observations, predict how each of the graphs of the functions below would be different from the graph. So we're supposed to make a prediction. I'm going to box in what we're supposed to do. State the changes that will be made to the basic graph. This is more instructions about the prediction. So these go hand in hand. We've done that. That's what this is right here. It doesn't actually say to graph it, which the directions should, because I wanted you to graph it. State the domain and range. So we have to state both the domain and range. We have not done that. The domain are all the x values that we can put into this function. And if you look at this, the graph goes to the far to the right as 1, and it goes left forever. So the domain, when we write domain, we go small to big. Domain then would mean from left to right. So where do we start from the left? Well, we're starting all the way on the left. All the way on the left is negative infinity. That means go left forever in this context. When do we stop? We stop going to the right when we get to 1. Does it include 1? Yes. A parenthesis means it doesn't include the number. A bracket means it includes the number. Negative infinity is not a number, so it always gets a parenthesis. Range, it's how far up and down the graph goes. We always go small to big. So the graph starts here at negative 3. Does it include negative 3? It sure does. When does the graph stop going up? It never does. It continues going left and up forever. So it goes to a positive infinity. Domain, range. Domain negative infinity to 1. Range negative 3 to infinity. We have just finished that problem successfully. Let's do the next one. Once again, the direction should have also included graph it. Once again, we do not want the coefficient of x to be negative, and it isn't. So we're good there. So 1, are there any reflections? There's a vertical reflection. This here gives us a vertical reflection. Are there any dilations? Are we multiplying a number on the outside or on the inside? The answer is no. So there's none of those. Are there any translations? Sure, we're going to translate to the right horizontally 1. There's a point in me always saying horizontal and vertical that we're going to be getting to here shortly. And we're going to be translating vertically up 3. When we graph this, let's put the vertex on first. The vertex is normally at 0, 0. We're going right 1 and up 3. So that means that we are going to be right here. That's our starting point at 1, 3, our vertex. There's a vertical reflection, there's no dilation. So a vertical reflection means instead of going up, we go down. Instead of going down, we go up. So normally we're going to go to the right 1, up 1, but now we're going to go right 1, down 1. Normally we go to the right 4 and up 2. Now we're going to go down 2 because the square root of 4 is 2. We go to the right 9 and down 3. It's going to put us someplace over here. That is the graph. We haven't found the domain and range. Domain starts at positive 1, it includes it, and it goes to the right forever. Starts at 1, goes to the right forever. The range, since this goes right and down forever, we want to go from small to big. The range goes from negative infinity until it gets to 3, then it stops. For the range, negative infinity means down, positive infinity means up. For the domain, negative infinity means left, positive infinity means to the right. Now let's look at this formally. So I will stop this video and make a second part, just to give you a sense of relief, but then a sense of shock when you see this as a second video. That concludes the introduction to this section, where we came at you sideways a little bit. We looked at different graphs and see if you could make some conjectures about how the numbers and negatives are affecting the graph.